Regression basics. Sample data, driver's age, and the maximum legibility distance of road signs. Research question: is there a linear relationship between the driver's age and the maximum legibility distance of road signs? We have data from 11 drivers. These are the ages, they are the x variables, the explanatory variable, and the maximum legibility distance in feet is the response variable or the y variable. First thing we need to do is calculate the sum of the ages and the distances. Next, we compute the degrees of freedom, in this case the number of observations, which you shall call df, degrees of freedom. In this case it will be n, the sample size, equal to the count of the range. And now we can calculate the average age and the average distance, and we shall call that the mean. In this case it will be x bar and y bar. X bar equals the sum divided by the degrees of freedom. Copy the equation. Now we have the mean x bar, we have the mean age as 47 and the mean legibility distance is 425. Next, we calculate the distance of each of these observations from their mean. We'll call that the difference, the x difference and the y difference. The x difference equals the x observation minus the mean x observation, anchored with the row anchored so that we may copy these things down without moving the reference cell down. And we copy that over to the y and down for all of these observations. We now have the differences. For variance and covariance, we need to calculate the products. X diff times x diff, y diff times y diff, and x diff times y diff. So x diff times x diff equals x diff times itself. And copy that over to y, and it'll do that for the y's. This is E4 times E4. This one is D4 times D4. For the cross product, x diff times y diff equals x diff times y diff. There. Now we copy these equations all the way down. In this case, and we sum them. Let's copy this sum equation across, and the degrees of freedom in this case is going to be equal to the number of observations minus 1, because the subtraction of the mean from the data takes away 1 degree of freedom. And now we can compute the mean, the average of these numbers, the average products. That's the sum divided by the degrees of freedom equals the sum divided by the degrees of freedom. There. And copy that across. Now we have 440 as the variance of age, 1543596 as the variance of distance, and minus 1907.56 as the covariance between age and distance. We can now take the square root of the variance, and that gives us the standard deviation, equals SQRT of there. Now we have the standard deviation of age as 20.98. The standard deviation of distance is 124. We're now able to compute a lot of very useful things. For instance, the R, the correlation coefficient. It's equal to the covariance divided by the product of the standard deviations. This times that. And R squared is called the coefficient of determination, is simply equal to R times R. There. We can also calculate the regression coefficient B. B, the regression coefficient, is equal to the covariance divided by the variance of X. It's 4.32983. And we can calculate the regression statistic A, called the y-intercept, as equal to the average value of y minus the average value of x times the regression regression coefficient, and 632. We can now write our regression equation. The distance equals A plus B times H. This is our regression equation. We now set up the sum of squares accounting, compute the F statistic and the p-value. So source, sum of squares, degrees of freedom, mean squares, F and P. The total sum of squares is the sum of squares of y. The degrees of freedom is 10. The mean sum of squares simply equal to the sum of squares divided by the degrees of freedom. We did that computation once before, but we do it again. And the sum of squares explained by our linear model is r squared. R squared is 53%. 53% of the total sum of squares is explained by our linear model. Distance equals 632 minus 4.32 times age. So the sum of squares due to the model equals r squared times the total sum of squares. And the degrees of freedom is the number of x variables. In this case, just one, age. So the degrees of freedom is 1. And the mean sum of squares equals the sum of squares divided by the degrees of freedom. And the remainder is called the residual sum of squares, what remains. By subtraction is equal to the total minus the model, and that 71765 is a residual sum of squares. The degrees of freedom we get by subtraction. The residuals have a degrees of freedom of 10 minus 1, or 9. That gives us a mean sum of squares equal to the sum of squares divided by the degrees of freedom, or that. We can now compute the F statistic. The F statistic is the ratio of the model mean square divided by the residual mean square equals model mean square divided by residual mean square, 10.35. The p-value equals F dist of this F statistic, comma, the numerator degrees of freedom, comma, the denominator degrees of freedom, close paren, hit return, 0.0105. We have now completed our regression analysis. We have the regression equation, we have correlation, r squared, and we have the sum of squares accounting the F statistic and the p-value, less than 5%, reject ho. The data provides sufficient evidence that there is a linear relationship between age and maximum legibility distance. Of course, we have to check for assumptions. Is the linear model valid? Are the residuals do the residuals conform to the assumptions? The assumptions is that the residuals are random and that they are normally distributed. We shall check for assumptions in a different video. Thank you for watching.